Hello, are you ready? Do you have momentum? Then fasten your seatbelt because this is about collisions. Let's start by considering Newton's third law. That says that forces come in pairs between objects. The force of object 1 onto object 2 is the same as in magnitude, but opposite in direction as the force of object 2 onto object 1. But we can write these forces as mass times acceleration. Mass of object 1 times acceleration of object 1 is equal to minus mass of object 2 times acceleration of object 2. We already saw that these two accelerations will be different in general depending on the ratio of the masses of the objects. The acceleration can be written as the derivative of the velocity with respect to time. And because the mass is constant, we can rewrite Newton's third law in terms of the derivative of mass times velocity. This is the linear momentum of each particle, so with a bit of rearrangement, we end up having that the derivative with respect to time of the total momentum of the system is zero. This implies that the total momentum of the isolated system is conserved in time. This is the conservation of linear momentum. And because all forces come in pairs and involve two objects, and because they satisfy Newton's third law, this can be generalized to any arbitrary number of forces. So, whenever there is a collision, there is conservation of linear momentum. Let's see this in an example. Let's assume we have a collision. This collision will conserve the linear momentum. Something we need to indicate here is that part of the energy of this system before the collision can be dissipated in the collision. This can happen as the collision might deform the objects, or the collision can produce sound or increase the temperature of the colliding objects. So energy might not be conserved, but momentum always. If the collision conserves the energy, we call that elastic collision. If the collision does not conserve energy, we call that inelastic collision. If after the collision both objects merge into one, we say that it is a perfectly inelastic collision. Let's go to the example. Assume we're playing billiards. Ball 1 is moving horizontally and strikes ball 2 initially at rest. Before impact, ball 1 was moving at a speed of 3 meters per second, and after impact it is moving at half a meter per second at 50 degrees from the original direction. If the two balls have equal masses of 300 grams, what is the velocity of ball 2 after the impact? First, let me draw a scheme of the collision and the initial data we have. I will decompose the final velocity of ball 1 in x and y components. I will now apply the conservation of linear momentum. So m1v1 is equal to m1v prime x1x, where the prime x reference to after the collision, plus m2v2 prime x. The same for the y-axis. Because both masses are equal, those terms cancel and we end with two equations for the velocities. I write the components of v2 y prime and v2x prime in terms of v2 prime and the angle of ball 2 with the horizontal. Now I can divide these two equations and get that the angle is 8.1 degrees. Now I substitute in the previous equation and find that the speed of ball 2 is 2.7 meters per second after the collision. Now let's check what happens with the energy. Because the collision takes place on a leveled table, the potential energy does not change in the process, and we can assume it is zero at all times. So we only care about kinetic energy here. Initially, the kinetic energy is 1/2 m1 times v1 squared. Finally, it is 1/2 m1 times v1 prime squared plus 1/2 of m2 times v2 prime squared. If we do the math, we get that initial kinetic energy was 4.5 m, and finally we get that the kinetic energy is 3.77 m. So the energy is not conserved and the collision is inelastic.